The diameter of the observable universe spans a total of 93 billion light-years across. Within this daunting expanse of starlight and wonder sits the Milky Way galaxy, merely a pinprick of light in comparison. And even smaller still is a humble blue sphere, called Earth, our home. My name is Daniel Danielson, and this is Space Stuff. Wait, Neil, space stuff? Oh, f*** all.
While there are exceptions, stars tend to be classified based on their surface temperature, color, brightness, and size. Not all the stars are listed because there are too many to get through without Neil having a stroke. Brown dwarfs, or stellar stillborns, f*** you, Neil, are too small to be a proper star, possessing the size of Jupiter but 13 times as dense. They radiate between 32 and 3300 degrees and have an as yet unquantifiable lifespan. Brown dwarfs are too cold to release visible light, so astronomers can only find them using infrared cameras. There is even some debate that these objects might actually be made of dark matter. Orange dwarf stars make up about 11% of stars in the universe, burning up to 9,000 degrees and which live up to 73 billion years. Red dwarf stars make up 73% of all known stars, in part because of their relatively low temperature, capped at 6,300 degrees, means they burn for between 70 billion and 10 trillion years. Just like these lists. Blue giants burn between 17,000 and 53,000 degrees, and they burn relatively quickly, using up all the fuel in the core within 100 million years before expanding to become a red supergiant. You know what's even hotter than a blue giant, Neil?
Right.
Martha Redgrave. I slept with her, you know.
Oh.
You're just jealous. Red supergiant stars are the death throes of a blue giant. When all the hydrogen in the core has been converted to helium, it starts burning the next layer of hydrogen, expanding to massive size in the process, and burning through all its remaining fuel in the following 3 to 100 million years, before going supernova. Their short lives mean they make up only 0.0001% of stars. Our star, also known as Sol, is a yellow dwarf star. These types of stars are easy for astronomers to identify on account of them being both small and yellow. Truly, the imagination of the scientific community knows no bounds. Yellow dwarfs make up just 10% of known stars, and burn steadily for somewhere between 4 and 17 billion years at up to 13,000 degrees. Our Sun will burn hydrogen at its core for 10 billion years before swelling up to become a red giant and engulfing the orbits of the first 3 planets, incinerating them. Because none of it, the girl you didn't ask to the dance, the promotion you got at work, your wedding, the birth of your children, the vacation you took, the home you bought, watching your children grow up, become adults themselves and flourish. The words you didn't say to your wife. The words you didn't say to your second wife. F***ing Martha Redgrave. Even this recording session. None of it ever f***ing mattered.
After burning for millions or even billions of years, eventually the largest stars in the night sky exhaust the resources within their core, resulting in a true spectacle of the cosmos. The largest explosion in the known universe, the supernova. Only 1% of the energy given off by a supernova is radiated by visible light. But even this small fraction of potential is equal to the amount of energy that our own sun will produce in its 10 billion year lifespan. Ugh, Americans. Even in a documentary, you insist on shoehorning in an explosion. What's next, Neil? Shall I put on some plastic antennae and talk about aliens and ray guns? No, I don't want any water. The gin will do just fine. You know who you're beginning to sound like, Neil? Helen. You're that irritating. Yes, that's right, I said Helen. And you know how horrible Helen is. What do you mean you don't know Helen? Prior to the supernova's ignition, a star maintains its spherical shape when the thermonuclear forces of the star's core pushes against its own gravitational forces. Once the star has burned up all the available resources within the core, the thermonuclear forces within are quickly overwhelmed by gravity, triggering core collapse. The resulting shockwave is so powerful that it actually kickstarts a brand new process of nuclear synthesis, creating heavy elements. In fact, any known element which is heavier than lead is almost exclusively created in a supernova. The deposits of heavy metals in the Earth has brought scientists to the conclusion that one of these massive shockwaves was responsible for providing the energy and upset of matter that sparked the creation of our Sun and solar system. But once collapse has occurred and the shockwaves have blasted through space is when the real show begins. Because if the remains of a stellar core still has sufficient mass, the equivalent of 3 of our suns or more, the remnant will implode once more, creating a stellar black hole. Not all stars are large enough to trigger a supernova, however. White dwarfs, for instance, typically lack the energy levels necessary to ignite the explosion, and must instead accrete nearby objects such as asteroids or dust clouds to begin synthesizing elements once more. After a multi-million-year process of converting the hydrogen in its core to iron, gravity overwhelms the diminutive star, finally causing core collapse, and thus the supernova is born. An awful lot of work just to blow yourself up, but who am I to judge? We all know what I did on my tour of Australia. Popularized by Albert Einstein's theory of relativity, a black hole is a region of space wherein gravity is so powerful that not even the speed of light, the physical speed limit of the universe, is sufficient to escape it. If one were to observe an object being drawn into a black hole, they would eventually see it slow to a halt, suspended in space, indicating that the captive planetoid has reached the event horizon, an astrophysical boundary through which light cannot escape, rendering anything beyond it invisible to us. Because of this, some consider what happens inside of a black hole to be the greatest of all scientific mysteries. A gaping mass in the universe that swallows everything, trying to desperately escape its grip. Do you know who that sounds like, Neil? Why, yes, Neil. It's Helen. You're learning. She took the house and the dog, Neil.
Don't tell me what's polite. While it is impossible to get an accurate number, scientists estimate that there are between 10 million and 1 billion black holes in the Milky Way alone, each varying enormously in both size and strength. Micro black holes are smaller than one stellar mass. Didn't we just say a stellar mass was the size of the Sun? That's a bit of a broad range, isn't it? As far as I know, a great number of things are smaller than the Sun. No, Neil, I didn't pay attention in science class. I was too busy not being a nerd. Oh, you're no fun. Look, is it too much trouble to add something? Must have hurt you to do that, really? Couldn't spare the moment? Dummy. Well, I think that if anyone's slowing us down, it's you. I'm simply offering a suggestion. He's just so adorable. Let's see here. Mass is the amount of stuff in an object, whereas the size is how much space that object takes up. Did you just write a lazy title drop, Neil?
Fuck you.
I don't like you either, but at least I'm being a professional about it. Supermassive black holes formed when several close proximity stars collide with one another, collapse in on themselves, and the resulting black holes collide again, creating a black hole of incomparable size. The largest of these behemoths is approximately 21 billion solar masses and is located in the brightest galaxy of the Leo cluster. Supermassive black holes reside at the center of nearly all large galaxies, including our own, the gravitational force of which actually holds said galaxies together in their orbit. Dormant black holes are merely black holes that are not currently feeding on any nearby celestial objects. Contrary to popular belief, the universe is actually in very little danger of being relentlessly absorbed by black holes. Regardless of its size, a black hole is only able to attract objects that lie within its gravitational range. Being that space is simply so vast, and the distances between individual black holes is so wide, their gravitational ranges rarely overlap. And while it is true that black holes grow larger as they absorb matter, they also grow smaller when deprived of a steady food source in a process known as black hole evaporation, wherein the black hole in question will continue to shrink until it is simply nothing. Oh, sorry, Neil. I was just daydreaming about Helen evaporating. It was pleasant.